Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of derivative as a function. So you have just been introduced to the limit definition of the derivative as a function. And now we're diving into just graphing derivatives and finding patterns. There's a ton of patterns in mathematics. In fact, all of mathematics showcases patterns. And so what you want to do is find out what those patterns are. And not just from a computational perspective, but also from a natural or a heuristic perspective, where you gain that ability to recognize patterns through just using mathematics. And you start to see things that normal people will not see. So let's go ahead and dive into that here. Let's graph some derivatives given functions. This is a skill that I think is so critical. My students can guarantee that something like this will be on an exam. So practicing this is of utmost importance. And I try to give you the easiest way to do this. So here's a function f right below, and we're supposed to graph f prime, the derivative. Now remember what the derivative stands for. The derivative just tells us the slope of the tangent line at any given moment. If you keep that in mind, this idea of graphing a derivative based upon a function being handed to you is actually not bad at all. I usually start by looking at where my tangent lines have a slope of 0. Now let me just showcase tangent lines here. So for example, right here, that's a tangent line. And right here, maybe I'll use just a thicker pen. This is a tangent line. That's a tangent line. Here's a tangent line. Here's a tangent line, and so on and so forth. Right? All of those are just tangent lines. This is how I would explain it if I was in a classroom. I would say this is like a road that you're driving on. Let me use a red for this just to showcase this. So you're on this road, driving. And when the tangent line is, let's say right here, is the direction your headlights are facing at that very moment. That would give you the tangent line to the curve at the point. It's the direction your headlights are facing. That's a good way of thinking about it. So let's go ahead and now estimate the slopes of each of those blue tangent lines, because the slopes of the tangent lines are the derivatives. And I'll even write their values. So for the easiest one is this guy. The slope right there, that slope of that tangent line is 0. And if I go over to maybe this guy right here, some of these are just gonna have to make up some numbers. So let's pretend as though that slope might be, oh, I don't know, maybe a slope of 1 or something like that. I mean, it kind of does look like a slope of 1. If you were to actually maybe allow this to fall linearly, you could see that it rose. So look where this point is. It's if this is a height of 1 up here, that's probably a height of 1/3. It looks like it rose about 1 when it ran 1. So yeah, that works out. I think that value right there, the slope is probably 1. And then this slope right here, well, okay, let's see what we did here. Okay, this height is, what do you think that height is? Maybe a 1.4. And the height right here is a 3. So let me make that 3 a little bit more visible. So we rose 3 minus 1.4 or 1.6 units. So that's how far we rose, 1.6 units. When we ran, so what was the run here? Not very much of a run, is it? About a 0.75 maybe. So when we ran, a 0.75. That's supposed to be a 5. So the slope there would be roughly, and I'm just ballparking this, a 1.6 rise over a 0.75 run. And so if you grab a calculator, and by the way, it's not going to be exact because I'm just really super ballparking this. But if I were to grab a calculator here, that's a slope of around 2 and some change. So I'll erase that and just say maybe a slope of 2.1 or something like that. 2.1. All right, let me get rid of all my handwriting there just to get it all out of the way so it's not annoying us. Now what I'm going to do is plot those points, because remember, the derivative function is just a plot of all the slopes of those tangent lines. So for example, the derivative function, I'm going to write this in red, the derivative function would at x equals 0 plot a height of 0, because at x equals 0 we're saying the slope of this tangent line is 0. And at x equals 1 we're going to plot a height of 1, because again it looks as though the slope at that point is a slope of 1. And at x equals, gosh, I don't know what this point is, but that value's whatever that value is, right? 1.75 maybe. At 1.75, it looks as though the slope is around a 2 and some change. Now again, because I'm ballparking this, it's not really the best. And if you go the other direction, so for example, let's do symmetric points. Just makes our lives a little bit easier. So if you go the other direction, if it's symmetric, which it does look symmetric, I would say the slope of that little blue line right there, it's going to be -1 because it's symmetric to the +1. And the slope at the very top, therefore, should be a slope of -2.1. Okay, and again, that's a massive ballpark on that, but let's go ahead and plot those. So at x equals -1, I'm going to plot a height of -1 for the slope. And at x equals -1.75, I'm going to plot -2.1, so something like this. Now, to be honest with you, these are actually not exact. Anybody who knows derivatives will know that they're slightly off, but that's okay. I'm not going to worry about it. But I connect those points, and it sure does look like they connect like a line. That's kind of neat, right? So this graph in red is going to be the graph of the derivative of that function, if everything I've done is correct. But because I was ballparking numbers, they're probably not totally correct. But I do want you to notice a pattern already. That black curve is a quadratic, is it not? It's actually x squared plus 1. And its derivative is a line, x to the first. And that is one of the first patterns you should start to see with derivatives. If you have polynomials, if the polynomial is the parent and the derivative is the child, then when you take the derivative, you lose that power. It looks like, at least from this, that you lose a power from the parent. So if it was a cubic, its derivative looks to be, now it's not a proof here, but it looks like the derivative would be a quadratic if the function was a cubic. Anyhow, I just find that to be very interesting. So graphing derivatives, finding patterns. Let's go ahead and try another one. Now, what I mentioned about polynomials doesn't really apply for anything else. So here is a function. And if you know your functions, then you know this is the natural logarithm or the logarithmic function. And this will be more of a ballparky type thing as well. So again, we're going to go ahead and look at the slopes of this curve. We're just going to try to estimate them. So I'll do that in blue again. So right around here, the slope of this, man, that's pretty hugely positive, nearing to positive infinity. Right here, it's less positive. Right here, it's definitely still positive, but just less. I'm trying to find good crossing lines. Right here, again, it's positive, but again, less positive. And right here, and especially here, they're tending to 0. So I'm going to apply some numbers here, and I'm going to make some numbers up actually. So like this one, the slope here, insanely positive. So maybe like a 3,000 or something like that. Maybe a 300. Let's say it's 300. The slope right there, likely not going to be that massive. As I'm looking at it, might be a 5 or something like that. Slope here could be a 1. I'm not saying it is. I'm just saying it looks like it could be a 1. And if that was a 1, then this is less. So I'm going to say this is roughly probably a half or something like that. And maybe this is a 4th. And maybe this is an 8th. This is definitely closer to 0, so like a 16th or something like that. I'm just making those numbers up just from ballparking, not because I know this function. I do know this function, but I don't want to cheat. I'm just going to go ahead and say, listen, they're getting smaller. You can tell the slopes are getting They're still positive, they're just getting smaller. Now let's plot those values as y values for the derivative. Well, I can't plot a y value of 300. That's way too far up, but I could start way up here at this x value and plot out a point that's at 5, even though that's not a 5. I'm just going to plot there. And here's a plot of a height of 1, because the slope is 1 at this point. Slope is 1/2 at this point, so I'll plot a 1/2. Slope we're saying is 1/4 at this point, and 1/16 at that point. So those red dots I'm going to go ahead and connect, hopefully smoothly, not miss them. I wish this was a piece of paper. It'd be easier because then I can turn my paper, but this is actually a laptop. So very difficult to turn a laptop when you have a bunch of other stuff on your desk. But there we go. Probably something like this is what it looks like. So that is a good graph of the derivative of this black curve. Now, if you take a look at this graph, definitely looks to have and will have a vertical asymptote along the y-axis here. So if you see that, then you can start kind of guessing for a pattern for what this derivative is. I'll let you try to guess that. We're not going to go into that in detail here, but there is actually a function that is represented by this red derivative. They didn't ask us to find the value of the derivative, so we're not going to bother because they didn't actually give us the actual function in black. All right, let's try another one. Oh, this is one of my favorites. Y'all know this one. Easy breezy. This is the sine curve, right? I will plot in there or label some points. This is pi over 2. Here's pi. Here's 3 pi over 2. This is definitely the sine curve. Whether they told us that or not, it is. Now let's go ahead and label some slopes in there. I always start with the easiest if I can find some easy ones. Here's a slope of 0. All right, m is equal to 0. And we also have a slope of 0 right here. That's pretty nice. M equals 0. And we also have other slopes of 0, right? So I won't label these now. I'll just kind of scoot them in there. But those are slopes of 0 as well. Then I look for easy increasing or decreasing slopes. So like right here, that looks to be, let me see if I can really justify it. If I were to continue this line up, it looks like it might cross at 1, 1, and 1, negative 1. At 1, 1, and negative 1, negative 1. And so it looks to me as though that slope is 1. And likewise, this slope right here, therefore, looks to be a negative 1. And you can go all day with this, right? So if that's the case, then this must be a slope of positive 1, slope of negative 1, slope of positive 1. All right, let's go ahead and plot those slope values as y values because we're plotting in red the derivative function. So at x equals 0, I'm going to plot a height of 1. At x equals pi over 2, I'm going to plot a height of 0. At x equals pi, I'm going to plot a height of negative 1. At x equals 3 pi over 2, I'm going to plot a height of 0. And then at x equals 2 pi, plot a height of 1. I'll go ahead and do the same thing in the other direction. At negative pi over 2, it's a height of 0. At negative pi, slope is negative 1. At negative 3 pi over 2, slope is 0. And finally, the slope of 1 at negative 2 pi. Now, if I were to connect these dots with a nice smooth curve and not screw it up too much, which is hard for me to do, honestly. Or should I say not to do? I can screw things up. You can see that red curve looks hauntingly familiar. It looks like the cosine. Now, this is not a proof that the derivative of the sine is the cosine, but it is very convincing that the derivative of the sine curve is actually the cosine function. So looking at functions and using them to graph derivatives you can see right now, can be very, very helpful to visualizing a possible pattern. Let's try yet another one here. Hop forward. This is actually really interesting. It's got what we would call corners in it. So let's go ahead and label some slopes. In this first, I'm going to start with the leftmost area here. This one, the slope is obviously 0 for that entire region. The next line, this piece right here, all of that, because it's a line, has the same slope. It rises 1, 2, 3 when it runs 2. So the slope of that is 3/2. And then we get back to a slope of 0 for a while. This one's kind of nice. And then we have a curve. Once you get to curves, it's a little bit different. This curve actually looks to get an infinite slope right there. Slope equals infinity. It's not that it equals infinity, but it approaches infinity. That's what it looks like to me. And then, actually, you know what it looks like? It looks like it approaches negative infinity. That it's falling, right? Slope is like that, but it's steeper. It's like that, but it's still falling. Okay. And maybe like right about here, the slope is like -5. It's negative because it's going down. Maybe right here it's a -1. And then by the time you get to here, the slope might be -1, I don't know, 1/4. But you can see it's going to be negative, but it's getting less and less so. Let's go ahead and plot these points as y values so that we can see our derivative. Well, in this first region right here, the derivative is always 0. So here's our derivative right here, always 0. And then suddenly the derivative snaps and becomes immediately, without smooth adjustment, becomes 3/2. And it stays that way for all of these x values. So there's this immediate jump. By the way, there's a hole right here and a hole right here. We'll talk about that in a moment. And then the derivative snaps, or the slopes snap to become 0 again. And again, I'll put a hole there and a hole there. I'll talk about that in a moment. And then all of a sudden, the derivative or the slopes look to be infinitely negative, and then they start to become less so until they get to an, oops, that was supposed to be a -1 right there, not a 1. So I'll do this, something like this. And the derivatives become, they're still going to be negative because it's still falling, but they're approaching 0. All right, I think that's pretty good. I'm going to put an arrow down at the bottom end of this just to say this keeps falling forever and ever and ever down here. So that red ink, very hard to see on the black there, sorry about that, but that red ink is the graph of the derivative. Now let's talk about why we have open holes there. The derivative is a limit, and the limit must exist on both sides for the limit to exist someplace. That is, if I said, oh, the limit as x approaches -1, -2, -3, as x approaches -3, that limit exists. For the slopes, then that means the slope from the left, which is 0, must be the same as the slope from the right, which is 3/2. That limit doesn't exist. It totally doesn't exist. They're two totally different numbers. It's 0 from the left, the slopes are, and it's 3/2 from the right, again, the slopes are. And so because those two slope limits don't match, the overall limit at -3 doesn't exist. So the derivative at -3 does not exist, because remember, the derivative is just a limit. So the derivative, f prime at -3 in this case, which is f at -3 plus h minus f at -3 all over h, and that's as a limit, as h goes to 0. That does not exist because the left and the right hand limits don't match. DNE. H from the left, the limit is not the same as the limit h from the right. That's not the best notation, but there you go. So that's why we have these open circles. It's because the derivative, which is a limit, doesn't exist at those points. Anyhow, really nice way to graph this. Again, something I pick on during exams. I really like these styles of functions. The final example in this section is, or in this video, I should say, is recognizing patterns with non-graphs, so with functions. So I hand you a couple functions. F of x is equal to x squared plus x plus 2, and g of x equals x squared plus x plus 4. And we're asked to take the derivatives of both of those functions. So let's go ahead. I mean, it's good practice, so might as well, right? You will have to use the limit definition of a derivative several times, at least many times, I should say, in calculus. Once you start learning the tricks, which most students who've gone through AP Calc know the tricks, but they don't really know all the theory. Once you get to know the tricks, you'll want to just use the tricks, but your professor, if they're worth their salt, will give you problems where you can't use the tricks. You have to use the definition. So you will still have to use this definition of a derivative all throughout calculus. Anyhow, we know the limit definition of a derivative is the following. So let's go ahead and substitute in. That's the limit as h goes to 0 of a big old fraction bar. F of x evaluated at x plus h is the following. Plus x plus h plus 2. And we're going to lose f of x. So lose x squared, lose the x, and lose the 2. This is all over h. Now, if you were to multiply that stuff out, limit as h goes to 0, you would get x squared plus 2hx plus h squared plus xh plus x plus h, sorry, plus 2 minus x squared minus x minus 2 all over h. And then just kill off any like terms. X squared here cancels with x squared there. X cancels with x. 2 cancels with 2. Nothing else combines, unfortunately. But you should notice that all the terms in the numerator have an h in common that you can factor out. Let me just double check my math. 2x plus h plus 1. Yep. And the h's here cancel beautifully. And you allow h to go to 0 because now you can do that through direct substitution. Direct substitution, you get 2x plus 1. Yay. Now, let's do the same thing for g of x. So g prime of x. Now I'm not going to write the definition. We have it up above, so I'm just going to write it this way. Is the limit as h approaches 0 of, let's figure out what g of x plus h is. That is x plus h quantity squared plus x plus h plus 4. And then we're going to subtract off g of x. That's all over h. Distributing through, you will get x squared plus 2hx plus h squared plus x plus h plus 4 minus x squared minus x minus 4. All over h. Killing off like terms, x squareds cancel, x's cancel, 4's cancel, and we get the following. Limit as h tends to 0 of, I'm factoring on h times 2x plus h plus 1 all over h. The h's cancel beautifully, and by direct substitution, we get this beautiful 2x plus 1. Okay, two completely different functions, f and g are. However, their derivatives are the same. So what happened? Well, that constant in the end, the 2 and the 4, there are two ways you can explain this. The easiest is mechanical. It's that, hey, you know, when I evaluated this difference quotient, which is what the derivative is really evaluating, when I evaluated this difference quotient, this 2 and that negative 2 were born to cancel each other off. That 2 came from f of x plus h. It's just the constant term in that. And I'm subtracting off f of x, which has the same constant term. So those 2's cancel. Just like the 4's, which are the constants in G, will cancel. Okay, that's believable. I'm with you 100%. I think you're correct. But there's another way you can view that. It turns out, and this is not a theorem you're introduced to yet, but I'm just going to state it. It turns out that if you want to find the derivative of a function, you could take the derivative of its components. That is, if I want to find the derivative of f of x, it would be the derivative of the first term plus the derivative of the second term plus the derivative of the third term. The derivative, remember, is it gives you the slope of the tangent lines at any given moment. Now, I'm not going to ask you what the slope of the tangent line to x squared is at any given moment, but I will ask you, what is the slope of 2 at any given moment? That slope is always 0. So that constant does nothing for our derivative. The derivative of that constant, remember the derivative just returns a slope of that curve. The derivative of that curve is 0. The slope of y equals 2, let me go ahead and just show you. Y equals 2. That's a horizontal line. Its slope is always 0. Likewise, with g of x, it had a component or a term that was constant. And remember, if you take the derivative of a function, I'm just saying this out loud right now, we'll have a theorem later on, but if you take the derivative of a function, it's the same thing as taking the derivative of each of its pieces and then adding those up. Well, the derivative of 4 is 0 because the slope of a line is 0. The slope of a horizontal line is 0. So that's why those two functions have the same derivative. It's because they're the same functions except for they're off by a constant. And it turns out that this is true for any kind of function. Doesn't matter if it is a polynomial or if they're a mixture of polynomials and trigonometric functions or whatever. Those constants in the end just don't matter for the derivative. They turn into 0 because they just add nothing. Their derivatives are 0. Anyway, really good pattern recognition on that. All right, I think we're done with this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.